Today we are going to discuss a new topic, that is hydrogen. It is a topic from inorganic chemistry, so it is very easy to understand. Much explanation not needed in this case. If there is a need of any explanation, I will give it to you. Okay, directly we can go to the chapter. Hydrogen is familiar to you. It is the most abundant element in the universe. And in the case of hydrogen, its position is a dispute. Where is the position of hydrogen? And we have considered it as a failure of a modern periodic table and also the Mendeleev's periodic table. They failed to give a good position for hydrogen. Now it is placed above alkali metals in the periodic table, and you know it is not belongs to first group. Hydrogen, to a certain extent, resembles both with alkali metals and halogens. It differs from them as well. It is unique in behavior and is therefore best placed separately in the periodic table. Now we can see what are the resemblances with alkali metals. Hydrogen, it has a lot of similarities with alkali metals. Some are pointed out here. What is the first one? Electronic configuration is 1s1 for alkali metals, ns1. Lithium, 2s1. Sodium, 3s1. The outer electronic configuration is same. 1s1, and for alkali metals it is ns1, outer electronic configuration. Second one, hydrogen and alkali metals combines in a similar manner with the halogens. They have a great affinity for halogens and readily combines with the halogens to form compounds of same molecular formula, NaCl, HCl. Combines with the halogen in a similar way, NaCl and HCl. Hydrogen shows +1 oxidation state like alkali metals. Most of the HCl hydrogen shows +1 oxidation. H2O hydrogen shows +1 oxidation state. And in the case of alkali metals, they will show +1 oxidation state always. During electrolysis, liberates from cathode like alkali metals. Hydrogen is liberated from cathode as alkali metals. Now, what are the resemblances with the halogens? Hydrogen is diatomic molecule like halogens, H2, F2. Hydrogen needs one more electron to get noble gas configuration like halogens. If hydrogen has one more electron, it has two electrons, that is the configuration of helium. Similarly, fluorine has 9 electrons. If it is getting one more, this is the configuration of neon. Hydrogen and halogens are non-metals. In metal hydrides, hydrogen has -1 oxidation state like halogens, NaH, NaBr. In NaH, hydrogen has -1 oxidation state. NaBr, bromine has -1 oxidation state. Now, dihydrogen, this is the most abundant element in the universe, as I already mentioned, and we can see hydrogen in the combined state in the earth crust, as it is in the form of water H2O, in the combined state. And in hydrocarbons, hydrogen is present. Carbohydrates, hydrogen is present. So hydrogen is present in the combined form, but free hydrogen is only a very small percentage. And hydrogen has 3 isotopes. Which are the 3 isotopes? Protium 1H1, deuterium 1H2, and tritium 1H3. Protium, deuterium, tritium. Deuterium also represented as D, tritium also represented as T. Now, preparation of dihydrogen, H2. Dihydrogen means H2, hydrogen, simply hydrogen molecule, that is dihydrogen. In the laboratory, we can prepare hydrogen by the action of acids on metals, dilute acids on metals. For example, zinc on HCl, zinc on HCl. In the lower classes, you may have prepared hydrogen for filling balloon from zinc pieces and vinegar. Vinegar is acetic acid. So when you put zinc pieces in vinegar, what happens? Hydrogen liberates. So that equation is given here. Zinc Zn plus 2H plus gives Zn2 plus H2. Hydrogen is liberated. Can also be prepared by the reaction of zinc with aqueous alkali. Zinc reacts with the alkali like acids. For example, NaOH2 form Na2SnO2 sodium zincate plus H2. Hydrogen is liberated. Now, commercially, how can you prepare hydrogen? Commercial production of hydrogen. There are several methods, and it is a familiar method for you. Electrolysis of acidified water. Electrolysis of acidified water results in the formation of hydrogen and oxygen. If you forgot any other method, you can remember it. Electrolysis of water. Because you are familiar with this method, 2H2, a liquid on electrolysis gives 2H2 plus O2, trace of acid or base. High purity dihydrogen is obtained by electrolyzing warm aqueous barium hydroxide solution between nickel electrodes. Warm aqueous barium hydroxide solution between nickel electrodes. If you want to prepare pure oxygen, electrolyze barium hydroxide. For pure hydrogen, electrolysis of barium hydroxide. Just remember in that way. And another method as a byproduct in the manufacture of sodium hydroxide. Sodium hydroxide is manufactured by the electrolysis of aqueous sodium chloride. In aqueous sodium chloride, Cl minus, H2O, and OH minus are present. Sorry, Cl minus, H2O, Na plus, or in otherwise we can say H plus is present. At the anode, Cl will be oxidized to chlorine, and at the cathode, H2 will be reduced to hydrogen. So liberation of hydrogen. So it is another method for the preparation, and the most common method is from hydrocarbons or from coal. From hydrocarbons, we can prepare hydrogen by the action of coke, red hot coke, at a high temperature in the presence of catalyst. An example is given here. CH4 plus H2O gives at 1270 Kelvin in presence of nickel, CO plus 3H2. It is a general equation to write the product of any organic compound. Here in the case of CH4, N is equal to 1. And 2n plus 2, 2 into 1 plus 2, 4, CH4. In that way. However, you have to remember at least one example. You remember the example of CH4 plus H2O gives CO plus 3H2O. The mixture of CO and H2 is called water gas. CO and H2 is water gas. As this mixture of CO and H2 is used for the synthesis of methanol and a number of hydrocarbons, it is also called synthesis gas or syn gas. The mixture of carbon monoxide and H2 can be used for the synthesis of a number of compounds such as methanol. Methanol can be prepared, formic acid can be prepared, such a number of organic compounds can be prepared. So it is known as syn gas. We can prepare hydrogen from coal. When coal is treated with the water, steam, red hot carbon and steam, you will get carbon monoxide hydrogen mixture. That process is known as coal gasification. The process of producing syngas from coal is called coal gasification. C plus H2 at 1270 Kelvin gives CO plus H2. The production of dihydrogen can be increased by reacting carbon monoxide of syngas mixture with the steam in the presence of iron chromate as catalyst. Here, carbon monoxide hydrogen mixture, it is very difficult to separate. If we can convert it into carbon monoxide to carbon dioxide, then we can easily separate carbon dioxide and hydrogen. For that, you have to treat this mixture, carbon monoxide hydrogen mixture, with water. When it is treated with water, what happens? CO will be converted to CO2 and one more hydrogen will be produced. You can add this equation with any of this. If you are adding this with this equation, C plus H2O will give CO plus H2. CO plus H2 plus H2O gives CO2 plus 2H2. In that way, you'll get hydrogen, increased amount of hydrogen, and the CO2 can be separated easily by dissolving it in water or by dissolving it in arsenite, sodium arsenite solution. And this reaction is known as water gas shift reaction. When water gas is treated with steam, more amount of hydrogen and carbon dioxide is produced. That reaction is known as water gas shift reaction. Properties of hydrogen. Dihydrogen is a colorless, odorless, tasteless combustible gas, highly combustible gas, H2. H2 is flammable, that will burn in oxygen. The hydrogen-hydrogen bond dissociation enthalpy is the highest for a single bond between two atoms of any element. High bond dissociation enthalpy. So it is relatively inert at room temperature due to this high bond enthalpy. So for the reaction of hydrogen, high temperature is needed. It does combine with almost all the elements. It accomplishes reactions by loss of the only electron to give H plus. It can give electrons and it will change it to H plus. Gain of an electron to form H minus. It can accept one electron to get noble gas configuration. And the third one, sharing electrons to form a single covalent bond. In this three-way it can react, and we can see some of the reactions here. Here, reaction with the halogens. It reacts with the halogens readily to give hydrogen halides. H2 plus X2 gives HX. Fluorine, chlorine, bromine, iodine. Hydrogen and fluorine, an explosive reaction between them. In the absence of light, that will take place. Hydrogen and chlorine react in the presence of light. With iodine, it requires a catalyst. Iodine can react with the hydrogen only in presence of a catalyst. Reaction with the oxygen, O2. Dioxygen means O2, oxygen. It burns in oxygen, already we mentioned, burns in oxygen readily to form H2O and liberates a heat energy of 285.9 kilojoule per mole. Reaction between H2 and O2 takes place at a high temperature. At ordinary temperature, it has no reaction. Reaction with the dinitrogen. With the dinitrogen, it forms ammonia. Dinitrogen means N2, 3H2 plus N2 at 673 Kelvin and 200 atmosphere in presence of iron gives 2NH3. Haber process. It is known as Haber process. In Haber process, instead of Fe, we will use Fe2O3, oxide of iron. Okay, now the next are reactions. Reaction with the metals. With many metals, it combines at a high temperature to yield the corresponding hydride. H2 plus 2M gives 2MH. Na plus H2 gives 2NaH, where M is an alkali metal. Reaction with the metal ions and metal oxides. Hydrogen will react with the metal ions or metal oxides and reduces these metal ions or metal oxides to the corresponding metal. The equation is explained here. H2 plus PD2 plus. PD2 plus is reduced to PD and H2 is converted to 2H plus. In general, a metal oxide of the type Mx or Y react with YH2 to form Xm plus YH2O. Just remember an example. That is enough. Okay, now reactions with organic compounds. Hydrogenation, reduction of unsaturated organic compounds. Hydrogenation of vegetable oils using nickel as catalyst gives edible fat. Example, vanaspati. Vanaspati is prepared by hydrogenation of vegetable oil. And a catalyst needed, that is nickel, hydrogenation. Hydrogenation can also be used for the preparation of alkanes from alkene. Alkenes, when treated with the hydrogen in presence of nickel, palladium, or platinum catalyst, alkenes will be converted to alkanes. Hydroformylation of olefins yields aldehyde, which further undergo reduction to give alcohol. Hydro formulation means H2 plus CO plus RCH double bond CH2. Addition of hydrogen and carbon monoxide to the double bond will take place. As a result, what you will get are CH2, CH2, CHO. This aldehyde can be reduced to alcohol. H2 plus RCH2, CH2, CHO gives RCH2, CH2, CH2, OH. It is an alcohol. Uses of dihydrogen. What are the important uses of dihydrogen? The synthesis of ammonia, manufacture of vanaspati. It is widely used for the manufacture of metal hydrides, preparation of hydrogen chloride. In metallurgical process, it is used to reduce heavy metal oxides to metals. Atomic hydrogen and oxyhydrogen torches find use for cutting and welding purpose. Atomic hydrogen and oxyhydrogen torches find use for cutting and welding purpose. Used as a rocket fuel in space research. Dihydrogen is used in fuel cells. It is used in the manufacture of bulk organic chemicals, particularly methanol, CO plus 2H2O. In presence of cobalt, catalyst gives CH3OH. Next, hydrides. There are three types of hydrides. What are hydrides? Compounds of hydrogen. They are known as hydrides. H2O is a hydride. Sodium hydrides. Name itself is hydride. NH3 is a hydride. That is hydride. Hydrides are classified into three. The first one is ionic or saline hydride. Ionic hydride or saline hydride. These are stoichiometric compounds of dihydrogen formed with most of the S-block elements. Means compounds of S-block metals and hydrogen. They are ionic or saline hydrides. They are ionic in nature. The ionic hydrides are crystalline, non-volatile, and non-conducting in solid state, but their melts conducts electricity. Example, sodium hydride, potassium hydride, lithium hydride, magnesium hydride, calcium hydride. All these are examples of saline hydrides. Saline hydrides react violently with the water producing dihydrogen gas. Sodium hydride reacts with H2 and forms NaOH and liberates H2. But LiH, it has no reaction with H2 because of its more covalent character. The reaction between H2 and LiH, that is slow. But LiH can be used for making useful compounds such as lithium aluminum hydride or lithium borohydride. They are well-known reducing agents. So LiH plus Al2Cl6 gives LiAlH for lithium aluminum hydride, that is a reducing agent. LiH plus B2H6 gives LiBH4, that also a reducing agent. Covalent or molecular hydrides. Dihydrogen forms molecular compounds with most of the p-block elements known as covalent or molecular hydrides. They are classified into three. The first one is electron deficient, second one is electron precise, and the third one is electron rich hydrides. We get an idea from the names itself. First one, electron deficient. Deficient means a less number of electrons. Where is this less number of electrons? Less number of electrons in the central atom. So an electron deficient hydride has less than 8 electrons in the valence shell of central atom. They act as Lewis acids. Electron deficient act as Lewis acids. That is electron acceptors. Example B2H6, BF3. All these are examples for electron deficient hydrides. Diborane, BF3. They are also Lewis acids. Electron precise hydrides. They have the required number of electrons in their central atom. For example, CH4. Carbon has 8 electrons. There is no excess. There is no deficiency. SiH4. Electron-rich hydrides, that is the third one, have excess electrons which are present as lone pairs. Example, NH3, H2. In NH3, one lone pair. In H2, two lone pairs are present. They are electron-rich hydrides. And the third one, metallic or non-stoichiometric hydrides or interstitial hydrides. These are formed by D-block and F-block elements. But at the same time, the metals of group 7, 8, and 9, they are D-block elements. They will not form hydrides. These hydrides can conduct heat and electricity. Some of the metals, for example, palladium and platinum, can accommodate a very large volume of hydrogen and therefore can be used as its storage media. This property has high potential for hydrogen storage and as a source of energy. You have to remember it. There are a lot of research for the effective storage of hydrogen. It is one of the method. A lot of research are going on there. Examples for interstitial hydride, LaH 2.87. Why it is 2.87? Because it is not through an ionic bond, not through a covalent bond. The hydrogen is entering into interstitial positions, interstitial or some other positions. However, it is not a bond actually. So the compounds are non-stoichiometric, we cannot see a stoichiometry. So LAH 2.87, YBH 2.55, TIH 1.5 to 1.8, VH 0.56, NIH 0.6 to 0.7. You study at least one example. One example is enough. Now water. We know water is very important in earth. There is life. Why? Because there is water. At moon or at other planets, the life is not possible. Why? There is no water. So water is very important. We discussed in detail the structure of water in the 4th chapter, so I'm not going to discuss it again. Now, structure of ice. In ice, one water molecule is tetrahedrally surrounded by 4 other water molecules, and the bonds are hydrogen bonds. One water molecule is surrounded by 4 other water molecules through hydrogen bond, and the shape is tetrahedral shape. So it has a highly ordered 3-dimensional hydrogen bond structure. Here you can see a lot of cavities. There are a lot of cavities or open space. Hydrogen bonding gives ice a rather open type structure with wide holes. So when ice melts, what happens? The hydrogen bonds will break and the molecules will enter into this open space. As a result, the volume of ice reduces and the density of water increases after melting. That is possible up to 4 degrees, and after 4 degrees, the density of water will decrease. To 4 degrees, water is denser than ice. The reason is when it melts, the hydrogen bonds will break and the water molecules will enter into the cavities or open space in ice. Chemical properties of water, amphoteric nature. It has the ability to act as an acid as well as a base. Water has a special property to act as an acid, acidic property, and also act as a base, basic property. Both the properties are there, therefore known as amphoteric nature. H2O react with NH3. NH3 is a base to form OH minus and NH4 plus. Here H2O acts as an acid. H2O plus H2S. H2S is an acid. Here H2O acts as a base to form H3O plus plus HS minus. You have to remember an example for the acidic property of hydrogen and also an example for the basic property of hydrogen. If you can remember this equation that explains both acidic and basic properties here. H2O, here H2O acts as an acid. This second H2O acts as a base to form H3O plus plus OH minus. So if you write this single equation, here explains the properties of water as acid and base. Second one, redox reactions involving water. Redox reaction. Water can act as an oxidizing agent. Also, water can act as a reducing agent. Water can be easily reduced to dihydrogen by highly electropositive metals. 2H2O plus 2Na gives NaOH plus H2. Sodium can liberate hydrogen from water. Sodium can liberate, potassium can liberate. Thus, it is a great source of hydrogen. We can prepare hydrogen from water using these highly active metals. So it can be considered as source of hydrogen. Water is oxidized to oxygen during photosynthesis. All of you are familiar with the reaction, photosynthesis. Here, water is oxidized to oxygen. 6CO2 plus 12H2O gives C6H12O6 plus 6H2O plus 6 CO2. With the fluorine also, it is oxidized to O2. 2F2 plus 2H2O gives 4H plus 4F minus plus O2. Another reaction, hydrolysis. You may heard about hydrolysis. There are a number of reactions. Due to high dielectric constant, it has a very strong hydrating tendency. It dissolves many ionic compounds. However, certain covalent and some ionic compounds are hydrolyzed in water. An example, P4O10, hydrolysis in water, hydrolysis in water, H2O to form H3PO4, phosphoric acid, H3PO4. SiCl4 undergo hydrolysis to form SiO2 and HCl. These are hydrolysis reaction. Another example, CaC2, calcium carbide undergo hydrolysis to form CaOH2 is calcium hydroxide and C2H2 acetylene. There are a number of examples for hydrolysis. The next one is hydrate formation, water of crystallization. You may have heard about water of crystallization. Hydrates. From aqueous solution, many salts can be crystallized as hydrated salts. The salts will be associated with the water. There are different types of hydrated salts. Coordinated water, coordinate bond. An example, CrCl3. In CrCl3, water is present as a ligand, CrH2O 6 times 3Cl minus. Coordinate bond is there. Coordinated water, interstitial water. Water may be present in the voids or free spaces of the crystal. Barium chloride, BaCl2 2H2O is an example. You have to remember these examples, they are very important. In some compounds, hydrogen bonded water, you can see hydrogen bonded water. The two may be present, coordinate bond and hydrogen bond. An example, COH2O 4 times SO4 H2O. Here this H2O is hydrogen bonded. Another one is COSO4 5H2O. Here 4 H2O are coordinated to copper CO2 plus and 1 H2O is hydrogen bonded. These are the important reactions of chemical properties of water. Now, an important thing related to water, there are two types of water, hard and soft water. You may have an idea about hard water and soft water. Not heavy water, hard water and soft water. Presence of calcium and magnesium salts in the form of hydrogen carbonate, chloride and sulfate in water makes water hard. Hard water does not give lather with the soap. So what is hard water? Which cannot give lather with the soap. Why it is hard? Because of the presence of soluble salts of calcium and magnesium. Which are the salts? Bicarbonates, chlorides and sulfates. Water free from soluble salts of calcium and magnesium is called soft water. It gives lather with the soap easily. So soft water gives lather with the soap. Why it is soft? Because here the soluble salts of calcium and magnesium are not present. We have to study about hard water. There are two types of hard water. First one is temporary hardness. Temporary hardness. Temporary hardness is due to the presence of magnesium and calcium hydrogen carbonates or magnesium and calcium bicarbonates. If bicarbonates only are present in water, the hardness will be temporary hardness. Can be removed by boiling. By simple boiling, temporary hardness can be removed. When a sample of water containing magnesium or calcium bicarbonate, here you can see it. When it is heated, the bicarbonate decomposes and form hydroxide and carbon dioxide. There hydroxide and carbon dioxide. Carbon dioxide is liberated, CO2. Two molecules of carbon dioxide is liberated. Then what is remaining? OH, MgOH twice is remaining here. So carbon dioxide is liberated. And this hydroxide is insoluble in water, so that can be separated. That can be separated. By filtration, we can separate. So the remaining water contains no bicarbonate, no soluble salt of calcium or magnesium. Insoluble salt is present. That will not affect the quality of water. Similarly, calcium hydroxide on strong heating, carbon dioxide liberates. Here, another possibility, calcium carbonate may be precipitated along with H2 and CO2. Here, calcium carbonate can be removed by filtration. Another method is Clark's method. In this method, the water with the temporary hardness is treated with the calcium hydroxide. This method is known as Clark's method. When calcium bicarbonate is treated with the calcium hydroxide, it will be converted to calcium carbonate. That will precipitate. We can filter and separate it. We will get a pure water. Magnesium bicarbonate, when treated with calcium hydroxide, that will be precipitated as calcium carbonate, magnesium hydroxide. These two are insoluble, can be filtered and separated. So these are the methods for the removal of temporary hardness. In the next class, we can discuss the method for the removal of permanent hardness and the remaining portion of the chapter. Okay.